Hi, I'm Dr. T and welcome to my office. So today I'd like to talk about nucleophilic substitution. In this case, we are going to be reacting an organic molecule and we are going to be replacing one functional group for another. And as such, let's jump in and look how it's done. So in nucleophilic substitution, we're going to start off and we're going to have ourselves a molecule. It's going to have a leaving group. And we're going to add into this guy a nucleophile. And usually this has a pair of dots as a lone pair because nucleophiles typically have lone pairs. And so what's going to happen, once again, this is one of two versions, S in 1 and S in 2. They're the same basic idea what's going on with the elimination. And in reality, you will compete these two. These will both fight for each other. So, in this case, the leaving group in SN1 is going to come off, leaving a carbocation. I've got my nucleophile hanging out, and then the nucleophile is going to attack. So, you know, that did that thing. That's going to attack there, and I'm going to get this guy. Quite often, the nucleophile and the leaving group may very well look very similar to each other, but you know, depending on the reaction conditions, which one's going to end up being the leaving group versus nucleophile. And of course, you get equilibriums and all kinds of funky stuff like that, just to make life fun. Okay, and likewise, SN2 is going to happen in one step. I'll have my leaving group. I'll have my nucleophile. The nucleophile attacks the carbon. The leaving group pops off. This will create a transition state where both are partially bound. Interestingly enough, when it comes to the three-dimensional arrangement of atoms, the stereochemistry of this, in this case you can get just about anything because you lose your stereochemistry once you go carbocation, that's flat. Whereas on this case, it always flips it because this is always doing a back attack. It's always going in from the backside. This is now nucleophile. The leaving group is floating free. And yes, so I have my nucleophilic substitution. Okay, so for this one, I want to look at a couple of examples, just kind of, you know, generic ones that you do quite often see. So one of which, let's look at a molecule that's going to have an ester functional group. And esters are an interesting one with nucleophilic substitution because they actually can go both ways with this. Okay, so in this one, what I can do is a hydrolysis. I am going to break this apart with water. So I'm going to add some water. And I'm probably also going to add some acid. The acid acts essentially like a catalyst. So in this case, the water is going to be my nucleophile. The bottom end of this carbonyl, these are what we call electrophiles. Generally speaking, every time I've been putting a plus sign on something, that's made an electrophile. Electrophiles are going to be nucleuses that have a little bit of an exposed nucleus. Their electrons aren't quite so dense, and they would be attractive to electrons. So in this guy is very negative up there, relatively speaking. It's still partially negative, don't get me wrong. It's not an anion. And the side is going to have a partial positive side, but carbonyls are notorious for this. They're very good electrophiles, and those will be denoted by the capital letter E sometimes. So the water is going to attack the electrophile, and then, hey, this can pop off, and so now you get this guy. So you've got your alcohol, now it's deprotonated, so this is going to very, very quickly go find itself a hydrogen and bond to that, because alcohols do not particularly like being anions. And then a base of some sort, probably another water molecule, is going to go ahead and take off one of those two hydrogens. Because at this point, when it's attached with 3 bonds, if you have an oxygen with 3 bonds, it's always going to be positively charged. So at this point now, we then finally just do a cleanup. This is, by the way, as I am drawing it, is SN2. The cleanup step is not part of the steps. The actual switch is, you know, kind of the core to it. And so then at this point, we now get our classic acid and alcohol. Okay, so let's look at another reaction, and I'm going to leave a couple of bits of this reaction out because it's going to require a catalyst, and that catalyst is going to, depending on which one you use, give you a couple of interesting responses. Okay, so in this case, I'm going to be doing another ester. Esters are nice to look at, not to mention we actually see these quite a bit. Okay, so I'm going to have my ester. Actually, I'm not going to have my ester. I'm going to have my acid and my alcohol, because this is typically where you're going to get these from. So you might be seeing this, of course, in polyester. Alternatively, you could be seeing this with your triglycerides or other fats, which have fatty acids and then alcohols that are esterified together. So similar reaction. We're going to see this one a lot when we look at biochemistry. Okay, so let's go for this one. This guy is going to go forward. I'm going to have the alcohol. The alcohol is going to attack my carbonyl carbon. Once again, there's actually a little bit more going on here depending on which catalyst you use. But anyway, so alcohol is going to attack the carbonyl carbon, and the water is going to come off. Once again, depending on exactly how you do this, this is an SN1 or an SN2. But I have now replaced my OH with my alcohol. And at this point, I'll have an OH minus, I'll have an H plus over here. So that's going to be charged, that's going to be charged, and then I do a little bit of a cleanup, which will give me the ester and some good old water. Because this gives me water as a byproduct, this is what we call a condensation reaction. Really, anytime I get a small molecule off as part of my reaction, we call that a condensation reaction. Typically, though, that's going to be water. Okay, one last thing with esters I want to show you, and that's called saponification. So in this case, we're going to do very similar reaction, but we're basically just going to go for it in reverse. I'm going to have my ester, and I'm going to react it with base. And we call this saponification because this is where you get soap from. Soap is basically fatty acids that have been treated with base. So I'm going to have my base of choice. And actually, you know what? I'm not going to call it OH. I'm going to call it KOH because that's usually what you're going to use. Sodium or potassium hydroxide, we're making soap. Okay, so this now means because I'm using this, I'm going to have some OH minuses present as well as some K pluses present. K pluses are spectators. They're not doing anything. Okay, so now one of the lone pairs is going to attack here. This is going to go over here, and now we get ourselves, see, double bond O, OH, plus OC minus, and this hydrogen is going to get moved off because this is a very strong base. This is going to attack the hydrogen, that's going to go off, that's going to become a minus charge. So now in the cleanup phase, we are going to have this guy. He's going to hang out with the potassium, and then you will have your alcohol left over. For fatty acids, of course, this is going to turn into your soap. You got nice long carbon chain sticking out past this carbon. It's going to hang out with usually sodium or potassium. And then the alcohol, for triglycerides, is glycerin, which is this guy. And that's a byproduct of soap or biodiesel production, which meant when biodiesel was starting to become big, the glycerin prices hit the floor because we had surplus glycerin. So with that said, this has been the kind of the top three, or kind of the core three reactions that we do as organic chemists. There are definitely others, which I will cover in a later video. And with that said, have a wonderful day, and I'll see you later.